Connecting above-ground steel tanks and pump bases to a ground ring offers several advantages. Firstly, it ensures equipotential bonding. This means all conductive surfaces, including the tank, pump base, and connected piping, are maintained at the same electrical potential. This prevents the buildup of static electricity, a critical safety measure, especially when flammable liquids are present, because static electricity can cause sparks or ignition hazards. Secondly, it provides ground fault protection. While the motor's equipment grounding conductor or EGC offers ground fault protection for the motor circuit, bonding the tank and pump base to the grounding system ensures that any stray currents or ground faults in the system are directed to the ground. The ground ring serves as the pathway. This prevents these currents from passing through equipment or, more importantly, personnel, enhancing safety. Thirdly, there is lightning protection. The ground ring serves as a low-impedance path for lightning currents to flow to the ground. By bonding the tank and pump base to this ground ring, you help protect against lightning damage. The ring directs lightning currents away from the equipment. Fourthly, and perhaps most importantly, it enhances safety. In the event of a fault or equipment failure, bonding ensures that all conductive surfaces remain at the same electrical potential, minimizing the risk of electrical shock to personnel working on or near the equipment. Although the National Electrical Code or NEC does not explicitly require bonding tanks and pump bases to a ground ring, it is generally recommended as a good practice. NEC Article 250.104b addresses this, stating that where there are two or more metal water pipes on the premises, and where these pipes are located in parallel, they shall be bonded together electrically. While this specifically mentions water pipes, the principle can be extended to include other conductive structures such as tanks and pump bases. In conclusion, bonding above-ground steel tanks and pump bases to a ground ring is a sound practice that provides several benefits, including equipotential bonding, ground fault protection, lightning protection, and enhanced safety. While it is not explicitly required by the NEC, it is highly recommended for optimal safety and improved electrical system reliability. Equipotential bonding is a cornerstone of electrical safety, especially in industrial settings where large metallic structures and equipment are prevalent. The primary goal is to eliminate voltage differences between conductive surfaces, preventing dangerous touch potentials that could result in electrical shock. The ground ring acts as a common reference point, ensuring that all bonded equipment remains at or near the same potential. Ground fault protection is another critical aspect. A ground fault occurs when an unintended electrical path develops between a live conductor and ground. Without proper grounding, this can lead to dangerous voltage buildup on equipment enclosures, posing a significant shock hazard. By bonding tanks and pump bases to a ground ring, any ground fault currents are safely conducted back to the source, tripping the overcurrent protection device and energizing the circuit. Lightning protection is also a significant consideration, particularly for above-ground tanks and equipment. Lightning strikes can induce high-voltage surges in electrical systems, causing damage to equipment and posing a risk of fire or explosion. A ground ring provides a low-impedance path for these surges to dissipate into the earth, protecting sensitive equipment and personnel. From a safety perspective, bonding all conductive surfaces to a common ground minimizes the risk of electrical shock. In the event of an insulation failure or other electrical fault, the ground ring ensures that fault currents are quickly and safely conducted to ground, tripping the circuit breaker and preventing dangerous voltage buildup. While the NEC does not explicitly mandate bonding tanks and pump bases to ground ring in all situations, it provides general guidelines for grounding and bonding that support this practice. NEC Article 250 covers the requirements for grounding and bonding electrical systems to ensure electrical safety. Section 250.4 outlines the general requirements for grounding electrical systems, while Section 250.90 emphasizes the importance of bonding metal enclosures and other conductive parts to create a low impedance path for fault currents. Section 250.104 covers bonding of metal water piping, and as previously stated, the principle is often extended to other metal structures like tanks. The absence of a specific requirement for tanks and pump bases does not negate the importance of proper grounding and bonding. Good engineering practice dictates that all conductive surfaces that could potentially become energized should be bonded to ground to minimize the risk of electrical shock. This is especially important in hazardous locations where flammable liquids or gases are present. In these areas, proper grounding and bonding are essential to prevent the accumulation of static electricity and the ignition of flammable materials. Several industry standards and guidelines also recommend bonding tanks and pump bases to a ground ring. These standards provide more specific guidance on the design and implementation of grounding systems for industrial facilities. The Institute of Electrical and Electronics Engineers, or IEE, for example, publishes various standards related to grounding and bonding, including IEE Standard 142, also known as the Green Book, which provides recommended practices for grounding of industrial and commercial power systems. The American Petroleum Institute, or API, also publishes standards related to electrical safety in the petroleum industry, which may include recommendations for grounding tanks and other equipment. In addition to these standards and guidelines, many companies have their own internal grounding and bonding policies that reflect their specific needs and safety concerns. These policies may be more stringent than the minimum requirements outlined in the NEC or other industry standards. When designing and installing a grounding system for tanks and pump bases, it is important to consider several factors, including the size and type of equipment, the soil resistivity, and the presence of any underground utilities. The ground ring should be sized appropriately to handle the anticipated fault currents, and the connections to the tanks and pump bases should be made with heavy-duty bonding jumpers. The soil resistivity can have a significant impact on the effectiveness of the grounding system. High soil resistivity can increase the impedance of the ground path, reducing the ability to dissipate fault currents. In areas with high soil resistivity, it may be necessary to use ground enhancement techniques, such as ground rods or chemical ground rods, to improve the conductivity of the soil. The presence of underground utilities also needs to be considered to avoid any interference or damage during the installation of the ground ring. The ground ring should be installed at a safe distance from any underground utilities, and care should be taken to avoid damaging any existing structures. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. The connections to the tanks and pump bases should be inspected periodically for corrosion or damage, and the ground resistance should be tested to verify that it is within acceptable limits. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. In summary, connecting above-ground steel tanks and pump bases to a ground ring is a prudent practice that enhances electrical safety and protects against equipment damage. It ensures equipotential bonding, provides ground fault protection, and mitigates the risks associated with lightning strikes. While not always explicitly mandated by the NEC, it is a widely recognized best practice supported by industry standards and guidelines. A properly designed and maintained grounding system is essential for the safe and reliable operation of any industrial facility with tanks and pump bases. It is crucial to understand the principles of grounding and bonding and to follow established best practices to minimize the risk of electrical hazards. Remember to consult with qualified electrical engineers and adhere to all applicable codes and standards when designing and installing a grounding system. The design and implementation of a ground ring system involves several technical considerations. The size and material of the ground ring conductor itself are critical to its effectiveness. Copper is often preferred due to its excellent conductivity and resistance to corrosion, but other materials like aluminum or copper-clad steel can also be used. The size of the conductor must be adequate to handle the maximum fault current that could be expected in the system. NEC Article 250.66 provides guidance on sizing grounding electrode conductors based on the size of the service entrance conductors. The ground ring should be buried at a sufficient depth to provide good contact with the earth and to protect it from physical damage. A typical depth is 30 inches, but this can vary depending on local conditions and regulations. The ring should also encircle the equipment being grounded, providing a continuous path for fault currents to flow back to the source. The connections between the ground ring and the tanks and pump bases must be made with robust bonding jumpers. These jumpers should be sized according to NEC Article 250.102c, which specifies the minimum size of equipment bonding jumpers based on the size of the circuit conductors. The connection should be made with approved connectors and should be protected from corrosion. The effectiveness of a ground ring can be significantly improved by supplementing it with ground rods. Ground rods are typically driven vertically into the earth at regular intervals around the perimeter of the ring. They provide additional paths for fault currents to dissipate into the ground, reducing the overall impedance of the grounding system. The number and spacing of ground rods will depend on the soil resistivity and the desired level of grounding performance. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. It is typically measured in ohm meters or ohm centimeters. Low soil resistivity indicates that the soil is a good conductor of electricity, while high soil resistivity indicates that the soil is a poor conductor. Soil resistivity can vary significantly depending on the type of soil, its moisture content, and its temperature. In areas with high soil resistivity, it may be necessary to use ground enhancement techniques to improve the conductivity of the soil. One common technique is to use chemical ground rods. These rods contain a chemical compound that leaches into the surrounding soil, reducing its resistivity. Another technique is to use bentonite, a type of clay that absorbs water and expands, creating a conductive paste around the ground rod. Testing of the grounding system is essential to ensure that it is functioning properly. The most common test is a ground resistance test, which measures the resistance between the ground ring and a remote earth reference point. The ground resistance should be as low as possible, typically less than 5 ohms. The test should be performed using a ground resistance meter, which injects a test current into the ground and measures the voltage drop. It is also important to perform visual inspections of the grounding system to check for any signs of corrosion, damage, or loose connections. Any deficiency should be corrected promptly to maintain the integrity of the grounding system. In addition to the technical aspects of ground ring design and installation, it is also important to consider the regulatory requirements. The NEC provides the basic requirements for grounding and bonding electrical systems, but local codes and regulations may also apply. It is important to consult with local authorities and to obtain any necessary permits before installing a ground ring. The installation of a ground ring should be performed by qualified electrical personnel who are familiar with the NEC and other applicable codes and standards. They should also have experience in grounding and bonding techniques. Proper documentation of the ground ring installation is also important. This documentation should include the location of the ground ring, the size and material of the conductor, the number and location of ground rods, the results of ground resistance tests, and any other relevant information. This documentation can be used for future maintenance and troubleshooting. The connection of tanks and pump bases to a ground ring is a critical safety measure that should not be overlooked. It helps to protect personnel from electrical shock, prevents equipment damage, and ensures the reliable operation of electrical systems. By following established best practices and adhering to applicable codes and standards, you can create a safe and effective grounding system that will provide years of reliable service. Let's delve into some specific scenarios and considerations related to grounding tanks and pump bases. Consider a large storage tank containing flammable liquids in a refinery. In this scenario, the risk of static electricity buildup is particularly high. The movement of liquids within the tank can generate static charges, which, if not properly dissipated, can accumulate and create a spark. This spark could ignite the flammable vapors inside the tank, leading to a catastrophic explosion. To prevent this, the tank must be effectively grounded to dissipate any static charges that may accumulate. The ground ring provides a low impedance path for these charges to flow to ground, preventing the buildup of potentially dangerous voltages. The bonding jumpers connecting the tank to the ground ring must be sized appropriately to handle the anticipated static discharge currents. In addition to grounding for static dissipation, the tank also needs to be grounded for lightning protection. Lightning strikes can induce high voltage surges in the tank, which can damage equipment and pose a risk of fire or explosion. The ground ring provides a path for these surges to dissipate into the earth, protecting the tank and its contents. Ground rods should be installed around the perimeter of the tank to provide additional grounding capacity. Now consider a pump base in a water treatment plant. In this scenario, the primary concern is electrical safety. The pump motor is typically powered by a high-voltage electrical circuit, and there is a risk of insulation failure or other electrical faults. If the pump base is not properly grounded, these faults can create dangerous voltage buildup on the pump enclosure, posing a significant shock hazard to personnel working on or near the pump. The ground ring ensures that the pump base is at the same electrical potential as the surrounding earth, minimizing the risk of electrical shock. The equipment grounding conductor from the motor circuit also provides a path for fault currents to flow back to the source, tripping the circuit breaker and energizing the circuit. The bonding jumper connecting the pump base to the ground ring must be sized appropriately to handle the anticipated fault currents. In both of these scenarios, it is important to consider the environment in which the equipment is located. Corrosive environments can degrade the grounding connections, reducing their effectiveness. In these environments, it is important to use corrosion-resistant materials and to protect the connections from the elements. Regular inspection and maintenance of the grounding system are also essential to ensure its continued effectiveness. Finally, let's consider the impact of stray currents on grounding systems. Stray currents are unwanted electrical currents that flow through unintended paths, such as the earth or metal structures. These currents can be caused by a variety of factors, including faulty wiring, unbalanced loads, and nearby electrical equipment. Stray currents can interfere with the operation of sensitive electronic equipment, cause corrosion of metal structures, and pose a risk of electrical shock. A properly designed and installed grounding system can help to minimize the impact of stray currents. The ground ring provides a low impedance path for these currents to flow back to the source, reducing the voltage gradients in the earth and minimizing the risk of corrosion or electrical shock. In addition to the ground ring, it may also be necessary to use other mitigation techniques, such as isolating equipment from the ground or using specialized grounding electrodes. Understanding the principles of grounding and bonding is essential for ensuring the safety and reliability of electrical systems. By following established best practices and adhering to applicable codes and standards, you can create a safe and effective grounding system that will protect personnel, prevent equipment damage, and ensure the reliable operation of your facility.